from there on we can capitalize.
Any changes that you want to share with us?
We are going to the same team.
Okay, all the best. Okay. So the news with the center Rajasthan brought and won the toss and they've elected to go first. So RR have won the toss. They have elected to chase. Down towards Sanju Samson's right. And he thinks there's a couple of men coming.
Okay, so I'll start the final week of this course. CE31 Structure Analysis 1 by Professor Amit Shah. I am one of the course teaching assistants, Trisha Chakravarti. I am a PhD student at the Indian Institute of Science, Bangalore. As always, we will start with a brief recap of the previous weeks. This course was divided into two phases: analysis of determinate structures and analysis of indeterminate structures. The first 6 weeks were dedicated to the first phase. The week one, we looked at types of internal forces, uh, bending moment, shear force, axial force, and torsional moment. Then common classification of elements like beam element, frame element, truss element, and boundary conditions like roller, hinge, fixed supports. Then we looked at structural indeterminacy and then how to draw bending moment and shear force diagrams, BMT and SFD. In week two, we focused exclusively on trusses, how we idealize trusses, how we idealize real world three dimensional trusses into 2D trusses that can be solved easily. And we look at the stability of trusses and solving member forces in a truss, solving the member forces and truss using two methods, method of joints and method of sections. In week three, we looked at the there are basically in a structure, our structure can give two different kind of responses, two responses that we are concerned about. One is the force of stress response that we looked at here. Here we solve with the member forces in a truss. We solve in each member, we will get a force, we will get the stress, and we will compare it to the yield stress of the material it is made of. So that is how we design. And the other kind of response is displacement or strain response or deflection. In real world structures that we build, deflection criteria is also very important. Maybe not as important as maybe not as important as the force response, but the displacement response also has some a role to play. We looked at the principle of virtual work, unit load method to determine displacements in truss. In week 4, we looked at the same for beams, deflection of beams using three main methods. One is the elastic curve equation method, where we go into the governing differential equation of the beam and get the profile of deflection as a function of x as it moves along the length of the beam. In the moment area method and the conjugate beam method, which we looked at in week 5, moment area method and conjugate beam method are both simplifications on the elastic curve method, and they are used in different kinds of situations, but all of these give identical results. Week 6 was focused on influence line diagrams, ILD. We looked at the Muller-Breslau principle, which gives us a qualitative ILD, and the ILD is basically when a force or load moves across a beam. We will look at how the bending moment and shear force varies. So from that, we can get absolute maximum bending moment and shear force under a point load, a series of point loads, uniformly distributed loads greater than or lesser than the span. Then, from week 7, we moved on to phase 2, analysis of indeterminate structures. Some points to be seen here are review of degree of structural indeterminacy, introduction to force and displacement methods, Maxwell-Betty's reciprocal theorem, method of consistent deformation, a force method, and review of kinematic indeterminacy and the displacement methods. That the displacement methods are currently going on. Week 7, week 8, and week 9 for the method of consistent deformation applied to the three main structural elements that we are concerned about: beams, trusses, and frames. Method of consistent deformation is a force method, and from week 10, 11, and 12 are for the displacement methods. Week 10 is just we looked at slope deflection method. In week 11, we looked at the moment distribution method, and week 12, that is today, we will look at the stiffness matrix method. Now we just have a brief overview of structural indeterminacy. Structures that cannot be analyzed using statics or equations of equilibrium only are called indeterminate structures. They need some other material properties to be solved because we need some additional equations, because we have more number of unknowns than equations, so we will need some additional conditions to be imposed to get a unique solution, and those we derive from material properties. The degree of indeterminacy is number of unknown reactions minus the number of equations of equilibrium. Now, there are two types of indeterminacy. Two types, even two classes of external indeterminacy and internal indeterminacy. And adding them, we get the total degree of indeterminacy. External indeterminacy is the total number of independent support reactions minus total number of available equations of static equilibrium. Available equations of static equilibrium is always 3 in a 2D plane and always 6 in a 3D space. Internal indeterminacy is total number of internal reactions minus available equations of equilibrium, and degree of total structural indeterminacy is sum of these two, external indeterminacy and internal indeterminacy. Here are some examples that we have looked at before. This is a cantilever beam. It has a fixed support and a free end. So the fixed support gives us three support reactions: Fx, Fy, and Mz. And as I said, in 2D plane, there are three equations of equilibrium. So this is a determinate structure because degree of structural indeterminacy is 3 minus 3 0. So if the degree of SI is 0, it is a determinate structure, and if it is negative, like there are lesser number of reactions than 3 in a 2D plane, that means it is an unstable structure, and we do not look at unstable structures. Unstable structures cannot stand itself, so we look at determinate and indeterminate structure. Indeterminate structure is safer, like this one. For example, this is a prop cantilever. If this prop somehow fails, this even if this fails, it will still be a stable cantilever beam. So this structure is safer than this structure. And here this is 1 degree indeterminate because there are four support reactions and three equations. Here, this is a frame that has six support reactions: three from this fixed end, three from this fixed end, and so 6 minus 3 is 3. And this is a frame with two hinge supports. Hinge gives two reactions each, Fx and Fy. Fx and Fy here as well. So 4 minus 1 3, 4 minus 3 1 is the degree of structural indeterminacy. These are the two approaches we use to solve indeterminate structures. Determinate structures can be solved very directly, as we have looked at before in the first few weeks, because indeterminate structures, determinate indeterminate structures, we can simply solve the support reactions, and we can find the bending moment, shear force, the deflections, anything, any response of the structure, we can solve it completely just by supporting the support reactions. And the support reactions we solve by using equations of equilibrium, because there are as many support reactions as the number of equations of equilibrium we have, right? So it is easy to solve. But if we have more number of reactions, the two approaches we follow are the force methods and the displacement methods. The force methods are also known as compatibility or flexibility methods. Redundant forces are chosen as unknowns, and additional equations are obtained by considering the geometric conditions imposed on the deformation of the structure. These are called compatibility conditions. Some of the methods that come under the force approach are methods of consistent deformation, unit load virtual work or unit load method that we looked at briefly in trusses, strain energy method, method of minimum potential energy, and flexibility matrix method. This method of consistent deformation is the only important one in this course. In future courses in advanced structure analysis, some other methods will also be important, but method of consistent deformation we looked at for beams, trusses, and frames. It is an important method. And the other approach is the displacement approach, also known as equilibrium or stiffness methods. Here, the displacement of joints are taken as unknowns, and equilibrium equations are expressed in terms of these displacements and internal loads. These equations are solved to give actual joint displacement from which redundant forces can be calculated. There are three methods that broadly come under this approach: slope deflection, moment distribution, and stiffness matrix. All three are relevant to this course. Though slope deflection and moment distribution method are more important, that we looked at the previous 2 weeks. Stiffness matrix method is basically a formulation. It is basically based on the slope deflection method itself, but it is a slightly different kind of formulation done in the form of a matrix, because computer codes are good with dealing with matrices, especially languages like MATLAB that are used by most civil engineers. And stiffness matrix, it is easy to formulate. So stiffness matrix is a framework of solving indeterminate structure that we can easily code. So a brief overview is given in this course, but mostly we look at stiffness matrix method and higher levels of that, like the finite element method, in advanced structural analysis courses. These are the difference between the two methods summarized. In the force method, unknowns are taken as internal member forces or reaction. In displacement methods, unknowns are taken as joint displacement. In force methods, to find unknowns, compatibility conditions are written, and in displacement method, to find unknowns, joint equilibrium equations are written. Now, when you have an indeterminate structure, how do we choose which approach we should follow? Force approach or displacement approach? This is the thing that guides us. In force method, the number of equation needed is a degree of static indeterminacy that we have looked at so far, and the number of equations required in displacement method is degree of kinematic indeterminacy, which is a different kind of indeterminacy. So of course, if the degree of static indeterminacy is less than the degree of kinematic indeterminacy, we would prefer to use a force method, because it is the number of extra equations that we need to solve. And here, if when degree of static indeterminacy is greater than degree of kinematic indeterminacy, we will prefer the displacement method. This is kinematic indeterminacy. We have looked at it last few classes, but here I will start with this because it is very relevant to the topic of stiffness matrix method. Because the number of independent degrees of freedom are the number of is the size of the stiffness matrix that we have to solve. So the degree of kinematic indeterminacy refers to the total number of independent available degrees of freedom at all joints. The degree of kinematic indeterminacy may be defined as the total number of unrestrained displacement components at all joints. Type of joints, for example, in a 2D truss joint, we know that since there are two force members in a 2D, any joint in a 2D truss can move in two directions, in x direction and y direction. There is no rotation involved. So there are two degrees of freedom available, delta x and delta y. In a 3D truss joint, again, all three translational degrees of freedom are allowed, delta x, delta y, delta z, but there are no rotation involved, so it has 3 degrees of freedom. In a 2D rigid joint, that is basically a frame or a beam joint, there are 3 degrees of freedom available. In 2D plane, delta x, delta y, and theta z, that is out of the plane rotation, like this kind of rotation. So this also has 3 degrees of freedom, but see, 3D truss and 2D rigid joint have uh, different 3 degrees of freedom, but both have 3 degrees of freedom. And a 3D rigid joint, that is a frame joint in 3D space, has all 6 degrees of freedom possible: delta x, delta y, delta z, 3 translational and 3 rotational, delta x, theta y, and theta z. So it is 6 DOFs. And the degree of kinematic indeterminacy, there are formulas for plane truss or 2D truss. This is the formula because at each joint, suppose there are j number of joints, at each joint we have 2 degrees of freedom. So the total number of degrees of freedom is 2j, and the total number of reaction support is re. Then those are restrained. The support reaction, like if there is a hinge support at one joint, both delta x and delta y is restrained at that point. If there is the roller support at some point, maybe the delta y is restrained at that point, at that node. So the total number of support reactions has to be subtracted because those are the restrained joints, and 2j minus re are the number of unrestrained joints, that is unrestrained degrees of freedom, that is the degree of kinematic indeterminacy. If by the exact same logic, for a space truss or a 3D truss, degree of kinematic indeterminacy is 3j minus re. Rigid jointed plane frame also is 3j minus re, and rigid jointed space frame is 6j minus re. There are some special cases. For example, if some members are actually rigid means that the delta x is restrained without a particular support reaction. The delta x itself is restrained. Then you will have a lesser degree of freedom, right? So the dk will be 3j minus re minus m dash dash. M dash dash is the number of actually rigid members, and in 3D it will be 6j minus re minus m dash dash. We will look at some examples to see how these formulas are applied. So this is a cantilever beam AB. There are two cases we will consider. One, the beam is actually flexible, and the other is that the beam is actually rigid. If the beam is actually flexible, then there are two joints. What are joints? Joint, every support point, every free point, every special point is a joint. But if there was a support in between, that would not be a joint. There are two joints, so 3 in J, and there are three support reactions at the fixed end: Fx, Fy, and Mz. So 3j minus re is 6 minus 3, 3. So the degree of kinematic indeterminacy for, if the beam is actually flexible, that is, this delta x is free at B, it will be 3. But if the beam was actually rigid, we have to subtract the number of actually rigid members, right? So there is one actually rigid member, the beam. So we will subtract that one and we'll get 2. And basically, then it was flexible. The degrees of freedom, these three are delta x at B, delta y at B, and theta z at B. And if you make it actually rigid, this delta x at B is taken away. So we can, the B can only displace downwards and it can rotate into the plane. Degree of kinematic indeterminacy for this beam. There are two joints. The J is 2, RE is 4 because there are two hinge supports, and delta x and delta Fx Fy, Fx Fy. So 3J minus RE is 3 into 2 minus 4 equal to 2. Now, these two support these two here basically delta x delta y are restrained at both these points. So these two degrees of freedom represent the rotation at A and the rotation at B. Now, if we consider AB is axially rigid, this degree of kinematic indeterminacy will not change because the axial displacement is already restrained here. So, in that case, we do not have to subtract -1. So, the rotational degree of freedom at A and B remains. This is another special case. In rigid jointed frames, some of the joints may be hybrid, then additional degree of freedom will be available. For example, hybrid means internal joint kind of thing. It is an internal hinge. Then for a 2D rigid jointed frame, dk will be 3j minus re minus m dash dash plus rr. Internal hinge gives an additional degree of freedom. And for 3D rigid jointed frame, it's the same formula, but rr here for 2D jointed frame will be the if there are m dash number of members meeting at a joint, then RR in 2D will be m dash minus 1, sigma m dash minus 1 that we have seen before. And in the 3D plane, a 3 will be multiplied with this, like RR will be sigma 3 into m dash minus 1. We will look at examples to make this clear. The number of independent degrees of freedom, the two span continuous beam. So here there are three joints, one, two, three, and how many support reactions? There is one roller, fx, fy here, fy here, and three from this fixed support. So there are five support reactions. So J is three, Re is five. So Dk is three into and three into three minus five. That is four. The kinematic indeterminacy of this frame here, there's an internal hinge, so this is a hybrid joint. And how many members are meeting here? Two. AB and BC are meeting at this hinge, so m dash is 2, and this RR quantity in the 2D plane will be 2 minus 1, so there is 1. And how many joints are there? 1, 2, 3, 4. The internal hinge also counts as a joint, and the number of reactions is 3 from the fixed support and 2 from the hinge support, so 5. So 3 into 4 minus 5 plus 1, that is 8. Here, degree of kinematic indeterminacy considering the beam to be flexible. Here there are three joints, one, two, three. As I said, the internal hinge has to be considered as a joint. And the number of reactions, 3 from C and 2 from A, so 5. And here m dash dash is 0 because there are no actually rigid members. And dash is 2 because AB and BC are meeting at this joint B. So RR is 2 minus 1, 1. And DK is 3J is 3 into 3 minus RE equal to 5 plus RR equal to 1. So the total is 5. This is a rigid jointed frame. Uh, if the beams are actually inextensible, that means we have four actually rigid members. These beams and columns basically the vertical members in a building structure are columns, and the horizontal members are beams. If you look around you, you will find out that there are columns and there are beams that you will see protruding out of the walls. So these are the columns 1, 2, 3, 4, 5, 6. We have 6 columns and 1, 2, 3, 4 beams. So this m dash dash here is actually rigid members equal to 4. That is important. And the number of joints here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 9. And number of there is no hybrid joint, so m dash RR is 0. But and now the support reactions. So fixed support gives 3 reactions, hinge support gives 2 reactions, and this is a different kind of support that may not have encountered before. This is a roller with 3 wheels. It roller always restricts the vertical deflection, so Fy it will give, but this also restrains the rotation. Unlike normal roller supports with 2 wheels and a triangle, the way we draw it, it does not restrain the rotation, but this restrains the rotation. So there are two support reactions here, two from here and three from here. So total 7 support reactions. Dk is 3 into 9 minus 7 minus 4, that is 16. And this is another one here. See, this is a protruding part. This also we have to consider as a joint. So there are 10 joints, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the number of support reactions, 3 from the fixed support, 2 from the hinge support, 1 from this regular roller support. So 3 plus 2 plus 1, 6. Here m dash dash and RR are both not into question. So decay is 3 into 10 minus 6, that is 24. There are 24 degrees of freedom and they have been drawn here basically. At these, Fx, Fy and Mz are all free. At this joint, nothing is free. No rotation, no displacement in x direction, y direction. At hinge support, it can rotate, but it cannot translate. And at the roller support, it can translate in the horizontal direction. It can also rotate, but it cannot move in the vertical direction. Now we will move on. Now that we have looked at kinematic indeterminacy, we will look into the concept of stiffness properly. Like Stiffness is the ability of the structure or material to limit deformation subject to an action. On a stress strain diagram that we have studied in class 11, 12, it is represented at the slope. That is, in a stress by strain is the stiffness basically. And stiffness is most pertinent to the serviceability of a structure such as deflection, cracking, and vibration. For example, in a spring, if you see, if this is a spring, you apply a force F and the deflection is delta, then simply put, the stiffness K is F by delta. This is just a very simple version. So, what does it represent? It represents force per unit deflection. So, it means that stiffness is the amount of force required to displace a structure by a unit length. So, if delta is 1, then stiffness will be the force. Then a stiffness matrix is basically it is a key concept in structural engineering that quantifies how a structure deforms under load. The stiffness matrix is a square matrix that represents the interrelation of forces at the nodes, defining the rigidity of a structural element in relation to its displacement. There are some properties of stiffness matrices. Order of stiffness matrix corresponds to total DOFs. As I said before, total DOFs is the number of is the kinematic indeterminacy. So singular stiffness matrix means structure is unconstrained and rigid, and it implies rigid body motion. Each column of a stiffness matrix is an equilibrium set of nodal force required to produce unit respective DOF. Symmetric stiffness matrix shows force is directly proportional to displacement, and stiffness matrix is always symmetric. By we already studied the Maxwell-Betti's reciprocal theorem earlier, so this is a consequence of that. That stiffness matrices are symmetric. Diagonal terms of a stiffness matrix are always positive. That is, force directed in say left direction cannot produce a displacement in the right direction. And the diagonal terms will be zero or negative only if the structure is unstable. Now we move on to the procedure of analysis using stiffness matrix method. The procedure of analysis using stiffness matrix method. Step 1. We have to determine the degree of kinematic indeterminacy, neglecting axial deformations. Then we identify independent joint displacement delta 1, delta 2, delta n. Step 2 is assign one coordinate in the direction of each unknown displacement of joint. We develop the stiffness matrix and find the inverse of the matrix. And then we remove displacements in the direction of coordinates and obtain locked structure. Find the forces developed in the direction of assigned coordinate due to given loading of the locked structures. Now, if P1L, P2L, PNL are forces developed in the direction of the coordinate, then the displacements delta 1, delta 2, delta 3, delta n will be K inverse of PL basically. So, this force is equal to K delta. That is the basic thing. Force vector is equal to K matrix into delta vector. So delta we get by K inverse of force. Now we look at a few examples. Using the stiffness matrix method, analyze the beam shown here. first we find out the kinematic indeterminacy. J here J is 3, 1, A, B, and C are the joints. Here the load application point is not considered as a joint, and RE is 5 because one roll there are two roller supports and one fixed support. So 3 plus 1 is 5, and they say that we have to consider the beams as actually rigid. So there are two actually rigid members. So M dash dash is 2. So the degree of kinematic indeterminacy is 3 into 3 minus 5 minus 2, that is 2. And what are these two we have to identify? So theta A and theta B are the free displacements, free degrees of freedom, because there is no axial deformation anywhere, and the vertical display deflection is restrained everywhere. So A can rotate, B can rotate, C cannot rotate. So theta A and theta B are the unknown displacements. We assign coordinate 1 in the direction of A and coordinate 2 in the direction of B. Now, to get the stiffness matrix, we need to get the first column. What we will do, we will give unit displacement in the direction of coordinate 1, and we will see the force developed in the first in at corresponding to corresponding to coordinate 1 and corresponding to coordinate 2. Now, the force developed corresponding to coordinate 1 is theta A is 1, and we have to ensure that theta B is 0. So as we know from before, using the fixed end moments, we get K11 is 4EI by 3 and K21 is 2EI by 3. And to get the second column, we will give unit displacement in the direction of coordinate 2, and we will ensure that coordinate 1 has no deflection. So theta B is 1 and theta A is 0. Okay, 1 2 is 2EI by 3. See, K21 and K12 have to be equal because difference matrices are always symmetric, and K22 is 4 has two contributions from this side and this side, so it is 4EI by 3 plus 4EI by 4 is 7EI by 3. And the stiffness matrix for the selected coordinates, that is theta A as 1 and theta B as 2, is this K12, K11, K12, K21, K22. So this is the matrix we get. Now we take the inverse of the matrix, and then what we have to do is we have to develop the force vector. The displacement vector is unknown, the stiffness matrix is known, and the force vector also has to be known. Now the force has to be known. So P1L and P2L are forces developed in the coordinate directions due to the given load in the log structure. Now we have some kind of loading, we have a uniform distributed load, we have a point load. We have to divide it in such a way that it is distributed in the coordinates, in the nodes. We cannot put a force in the middle of the beam. So I mean, this is where the fixed end moments come into play. We have looked at the fixed end moments before that. For example, if a moment is applied, if a force's point load is applied at the midpoint of a beam, the fixed end moments are PL by 8. So MAB bar is minus 10 into 3 by 8, and MBA bar is plus PL by 8. So 3.75. MCBC bar is 6 into 4 square by 12. Similarly, by using those formulas, like for UDL, we know that it is WL square by 8 minus and plus, and the total force vector we will get. The total forces we are concerned about here is the ones corresponding to the free coordinates. Since theta A and theta B are free, we need the forces as moment at A and moment at B. Moment applied at A and moment applied at B. That is minus this minus 3.75 and minus of 4.25 here. So this is the matrix equation we get. Delta 1 delta 2 is K inverse of P, and from that we get theta A is 2.22 by EI and theta 2 is 1.1875 by EI. Now we get the final end moments as we use in Stokes reflection method in exactly the same formula. Using this delta here is due to relative displacement between the 2 points, which there is not there. So MAB is MAB bar plus 2EI by L, 2 theta A plus theta B minus 3 delta by L, and like this we get the fixed end moments. And once we have the fixed end moments, we can just draw the bending moment diagram by superimposing them. This bending moment diagram is due to the applied loading, and this is due to the fixed end moments, and by adding them algebraically we can get the bending moment diagram of the entire structure. This is a frame. We have to solve using the stiffness matrix method. Here, so there are three joints, one A, B, and C. So degree of kinematic indeterminacy is 3 into 3 minus the number of support reactions is 3 from the fixed support and 2 from the 2 in the hinge support, so 5. And there are two actually rigid members, so 2. So this is dk is 2, and again here it is theta b, and so the free movements here are theta b and theta c. So these are our coordinate 1 and coordinate 2. To get the stiffness matrix, for look at the first column, we will give a unit displacement in the direction of the coordinate 1. Assume theta b equal to 1 and theta c equal to 0. So k11 will be 4ei by 5 plus 4e into 2i by 4. Here the moment of inertia is different for the two. You have to take note of that. This is I, this is 2i. So this is 14ei by 5, and k21 is 2 into 2e into 2i by 4. So that is ei. And to get the second column, we will give a unit displacement in the direction of theta c, and we have to ensure that theta c is 1 and theta b is 0, and we know that k12 is k21 by the Maxwell-Bettis reciprocal theorem, so that is equal to ei, and k22 is 4e into 2i by 4, that is 2ei. So the stiffness matrix for the kind of coordinates we have selected is this. And again, to get the moments, we have loading, we have a point load at not at the midpoint of this, at some point a, some distance a and some distance b from these 2 points. For that also the fixed and formula we know, p s square b by 8, right? P s square b by l square. So p12 and p2l, p1l and p2l are the forces or moments developed in the coordinate directions due to given loading in the locked structure. Locked structure means the structure with the degrees of the restraints applied. So MAB bar is minus P 2 square into 3 by 5 square is minus 36, and BA bar is 50 into 3 into 2 square by 5 square. And for BC and MCB we use a simple formula because it is just a uniformly distributed load. So WL square by 8 minus WL square by 8 plus WL square by 8. And so the load vector we get is, we will take uh, P1L is MBA minus MCB, so the MBC, so that is minus 56, and P2L is simply M bar CB, that is 80. And the K matrix we had, so the inverse we had found out. So delta 1 2 is K inverse of F. So from the F vector, so we get delta 1 as this. Delta 1 is here theta b, and delta 2 is theta c. So we get these two. The final end moments you can find out using MAB equal to MAB bar plus 2EI by LAB into 2 theta A plus theta B minus 3 delta by L. The delta here is 0. So the fixed end moment AB is minus 19.33. MBA is 57.46. So, and the MBC and MCB are similarly found out. So once we have the fixed end moment, again to draw the bending moment diagram, we just can superimpose the fixed end moments and the moment diagrams due to the applied loading. And here we know that for uniform distributed load we get a parabolic bending moment diagram. For point load we get a triangular diagram. So that is how we can get the bending moment diagram. And this is a 4-membered frame, and there are 5 nodes here. So 5 joints here, and the number of reactions here is 3 plus 3 plus 3 plus 2, so that is 11. And there are axial displacement, the m dash dash here is not 4 because the axial displacement of OD and OB are already prevented. Hello ma'am, my classmates here perform করছি। Yes, so here we have the degree of kinematic indeterminacy is 3 into 5 minus 11 minus 2, that is 2. And here we can see that the degrees of freedom here are that this O is free to rotate and A is free to rotate. There is no other degree of freedom. So theta O and theta A are the unknown displacement, and we say that theta O is 1 and theta A is 2. To get the stiffness matrix, get the first column, we give unit displacement in the direction of coordinate 1. So we give theta O is 1 and theta A has to be 0 here. You have to ensure that. So for that, K11 we get as, we add the contributions from all 4 elements because this O is connected to all 4 members. So 4E into 2I by 4 plus 4EI by 4. The moment of inertia here are different. This is 2, this is 1.5, and these two are II. So 4ei by 4 plus 4ei by 4 plus 4e into 1.5 I by 3. We know that at the fixed end it is the denominator has 4, and at a hinged end it is 3. So from that we get k11 is 6ei, k21 is 2e into 2i by 4, that is ei. And to get the second column we give unit displacement in the direction of coordinate 2. Theta a is 1 and theta o has to be 0. So k12 is equal to k21 due to by the reciprocal theorem, because the matrix has to be symmetric. And k22 here is 4e into 2i by 4, that is 2ei. So the stiffness matrix is this. We find out the inverse, and as usual, and we have to find out the forces moments developed in the coordinate directions. So we need the moment at o and the moment at a, and from that we get using this regular formula, because there is a uniformly distributed load applied here. So this is the force vector that we got, and from that we solve the theta delta 1 delta 2, that is theta 1 theta a, and then we get the final end moments like this. And these are the final end moments using the old formulas, and from that we can draw the bending moment diagram by superimposing the bending moment diagram. Due to this loading there will be a parabola, and due to the fixed end moments at all 5 of the nodes. So that's all. Thank you so much for this.